Hello and welcome to our brand new broadcast, Facebook Live, here at Astronomers Without Borders. I'm your host, Andrew Fazakis, the Night Sky Guy, here for AWB, as usual, hosting and guiding you through our Global Astronomy Month Festival. This is the 12th edition of the world's largest celebration of the night sky. And sharing the wonders of the universe is what it's all about, what we're all here for, our community, all under, of course, one sky. I'd like to welcome all of you to today's broadcast. Wherever you're watching, we've got the chat room open with all the comments. I'm looking at all of you here on my chat right now, and I'd like to say a big shout out to all of you wherever you're watching. We've got Sandia from Australia. We've got Suna from Turkey. We've got Leah from Netherlands. Welcome to the show. Astronorm from Philippines, our Philippines National Coordinator. Welcome, Norman. So nice to see you. We have Ashish from India, Elisabetta from Bucharest, Hafez from Malaysia, and we've got Reza from Tehran. Welcome. Wonderful for you to join us. Elizabeth from Minneapolis. So nice of you to, and Desta from Italy. I hope you guys having clear skies and doing some observing this Global Astronomy Month wherever you're watching. It's wonderful. It's great to see so many people from around the world tuning in. And of course, today in Global Astronomy Month schedule, as it is always annually, it's SunDay. It's the day we've set aside here at AWB to celebrate our own star. Of course, this is, in terms of astronomy, a lot of us think of course, the night sky when the sun goes down to look towards the heavens. But of course, the nearest star to us and the most precious star of all is our own sun at the center of our solar system. And it offers such amazing wonders and mysteries, not just for amateur backyard astronomers, but also for professional astronomers as well. And we're so fortunate today to have with us on our GAM schedule is a wonderful double presentation, actually, from two individuals who are associated with the National Solar Observatory. We've got Dr. Claire Raftery and John Williams, both of them working out of Boulder, Colorado with National Solar Observatory, working in the outreach and education on behalf of the Inouye Solar Telescope in Hawaii. And if you haven't heard about this facility, guys, I've got to tell you, this is the most magnificent, exquisite instrument to observe the sun. And it is bound to completely revolutionize our knowledge about our star, and some of the imagery already. The taste of what it has given us has been incredible. And I'd like to bring into our show our two guests, Claire and John. Welcome.
Thanks for having us, Andrew. It's really wonderful to be able to join you today.
Oh, it's so wonderful. And John, welcome to you too.
Hello.
Hi. And you guys are both in Boulder, Colorado right now?
Yes, that's right. Joining you from my home as opposed to my office, because like the rest of the world, we are also on lockdown due to COVID-19. Thanks very much. So one of the benefits, of course, is working on a Sunday morning, being able to join you from here as opposed to having to make my way into the office. So that's a nice thing. One of the bonuses.
Yes, I mean, this is really strange times we're living in with, of course, the pandemic and everything being virtual. But it allows us also. It's just such a wonderful opportunity to connect with people like yourselves around the world. Here at AWB, we're always excited to be able to learn new things, showcase these things to the world. And of course, today it's all about the sun that we're talking about. So, Claire and John, I'd really love for you to dive right in. I'm so excited to find out about the world's largest solar telescope and for you guys to give us a peek inside of some of the details there. So I'm going to hand it over to you.
Okay, thank you, Andrew. And we're really excited to share these details with you. So John is going to steer our presentation today. So while he's getting that set up, I will dive right in. So thank you for giving us the opportunity to chat to you and your members today. As you mentioned, my name is Dr. Claire Raftery, and I'm the Head of Education, Outreach and Communications for the National Solar Observatory. And NSO, as we call it, is a center that's funded by the US National Science Foundation, which is one of our federal agencies funding science. So I'm hoping that you may have seen the image on the right-hand side of this slide at some stage in the past. This was a picture that we released from the Inouye Solar Telescope last year, and it is the highest resolution picture of the solar surface that has ever been taken. We're going to dive into it a little bit today and just sort of explore a little bit more about this and how you go about running a solar telescope as large as the one that is being built currently in Maui, Hawaii, the Inouye Solar Telescope. So we're very fortunate in studying the sun. Unlike nighttime astronomy, first of all, we don't have to stay up all night to be able to see our stars. We can do this during the day. And second of all, the sun is the only object, the only star in the universe whose surface we can resolve with any kind of detail. And so we're able to use the sun as the Rosetta Stone for stellar astronomy as well as for solar astronomy. So we're able to take what we learn about the sun and its behaviors, and in particular its magnetic field, which it turns out is one of the most important drivers of all solar activity, and apply it to our understanding of the rest of the solar system. So you can see here, this is a schematic of what it is that we're looking at, because in order to get a picture as close up of the sun as we have, we can't take a picture of the entire solar disk. So the large picture that you can see in the background, that's a picture from NSO's other facility called GONG. the Global Oscillations Network group. And GONG actually is a series of telescopes that are located all over the world. We have 6 telescopes all the way around the world, and that means that we're looking at the sun 24 hours a day, 7 days a week. And so it means we're always able to see what's happening on the solar surface and in the low solar atmosphere. So the full picture of the sun there is from our GONG network, and then you can see the little square superimposed on the top of this. And this is the field of view of the Inouye Solar Telescope picture that I showed you on the previous slide. And if you can step forward, John. The thing about this is that we're able to zoom in so much detail on this particular picture that it's like we consider it like a microscope for the sun. So we're able to zoom in to see more detail than we've ever been able to see before in any picture ever taken of the sun. And the nice thing about this, or the important thing about this, is that there are details that we can now resolve finally that we've only ever been able to estimate using theoretical models. So we have beautiful models put together using computers and mathematics that replicate what we expect to see in these pictures. We've never actually been able to take a picture of these before. So this is showing detail like we've never seen anything before. So my favorite parts of this are sort of in the close to the top right corner. It almost looks like a maple leaf. So Andrew, I believe you're in Montreal, so maybe we'll be able to dedicate this to our friends up in Canada.
Yay to Canada.
John, if you can step forward again, there's just the reference points, because when you're talking about the sun, you know, it's so far away and it's so large, and you can fit 109 full-size planet Earths across the face of the sun. But what does that even mean? It's so hard to put these things in perspective. And to give you some scale for this, what we see in the box on the top right here is about the same size as the whole state of Texas. So that's just to give you a scale down there. And if you go forward one more time, you'll see that some of the tiniest details that you can see in this picture are about the same size as the whole island of Manhattan. So even though for us this is revolutionary in how, you know, how tiny and detailed these elements of the solar atmosphere are, they're still, you know, they're still kilometers, tens of kilometers across. So these are really, really enormous structures that we can see. And they're largely driven by, as I mentioned earlier, the solar magnetic field. So the sun is a giant magnet, and it is a very complex magnet. So you have a magnet not unlike, or a magnetic field not unlike a, you know, a refrigerator magnet that you would have. So you may have seen pictures of these in a school textbook where it looks almost like butterfly wings. But as the sun evolves through its solar cycle, it actually gets tangled up. Its magnetic field gets wrapped up in itself, and it bursts out through its surface, creating all of these beautiful patterns. We call these granulation patterns. And the magnetic field sort of pierces up through the dark channels in between the bright areas. So these are like bubbles. This is formed using a similar sort of technique to boiling water or boiling oatmeal. If you've seen that sort of structure, that sort of behavior, then this is very similar, obviously on a much, much larger scale. So we're realizing more and more that the sun's magnetism is really key to understanding its behavior and what drives the solar explosions, what we call space weather. And if we can move forward to the next slide, John, this is a photograph of the Inouye Solar Telescope, the outside of the telescope. And this will be the first solar telescope in the world, I guess technically, probably in the universe, that will consistently measure the sun's magnetic field in the corona specifically. So we've been able to measure the magnetic field on the surface. You may have seen black and white and gray blobby pictures of the sun. They're the sun's surface magnetic field. But being able to measure the magnetic field in the corona is actually something that we haven't been able to do with any consistency before. So it's a 4-meter solar telescope, and it's almost finished construction out in Maui, Hawaii. And it's being built by the National Solar Observatory on behalf of the National Science Foundation. And so 4-meter, you know, especially for folks who may be familiar with research telescopes from the nighttime realm, 4 meter might seem really, really small by comparison. But the difference is that you're focusing 4 meters of sunlight, and think about how close and intense light from the sun is compared to light from faraway stars. And so this is a compounded problem. There's lots of engineering challenges dealing with heat and other challenges like that. And so if we can go back to the slideshow, we can see that this telescope is going to be able to see the sun's details about 3 times higher in resolution than anything we've ever been able to see before. So the picture that we showed you a few minutes ago, that's just the first taste of what we're expecting to see from the telescope. Unfortunately, like the rest of the world, there was delays as a result of restrictions due to COVID. And so the construction schedule has been pushed out a little bit, but we're hoping that construction will wrap up by the end of this year, and that means that we will hopefully start to see a more steady flow of images coming from the telescope beginning maybe early next year. So we're all keeping our fingers very tightly crossed that everything goes smoothly and quickly with this. And as Andrew said at the beginning, this telescope, in combination with the NASA's Parker Solar Probe and ESA's Solar Orbiter, these 3 new missions are set to really revolutionize how we understand the sun and how we study the sun as well. So this is a really exciting time to be involved in solar physics. So if we move on to the next slide, I'll show you an artist's impression of the inside of the telescope. So to sort of walk you through what it looks like on the inside. So if we can step forward, we should zoom in on the top half of this picture. And what you can see here in this cartoon is the entrance aperture that is at the top of the screen here. This is just below the sun. It's the hole in the dome, so the rounded dome, and then we have the hole in the top. And this aperture helps to make sure that our light is nice and focused and streamlined, and that we're rejecting any stray light. And the light comes in and it bounces off our 4-meter mirror. So that's the kind of bluey silver oval in the center of the picture. This is the main mirror that is sort of the heart of what pushes this telescope into the next phase of advanced technology. This focusing 4 meters worth of solar energy is about the same energy that would be used by 2 domestic households at any given time. And so that gives you an idea of how much energy we're dealing with. So controlling that energy is a really big part of what we do. And so focusing, the light gets focused from the telescope up to what we call a secondary mirror, which is on the top left area of that dome. But before it gets to the secondary mirror, it goes through a piece of technology or piece of material called a heat stop. And this helps to reject extra light. It helps to remove the majority of the heat from the system, because the rest of the optics that the light is going to travel through are very delicate and need to be heat controlled. And so we need to make sure that everything is very stable and very consistent. And so the heat stop plays a really critical role in making sure that that happens. So once the light bounces off of the secondary mirror, and you may notice that unlike many telescopes, the secondary mirror is not in the light path of the incoming light. So unlike perhaps telescopes, reflectors that you may have at home, or other research level telescopes, the secondary mirror is offset from the light path of the incoming light in order to reduce stray light. So we want to be able to picture and image the solar corona. And for anybody who's ever seen a solar eclipse, the corona is very beautiful and very delicate and ethereal, but also very, very difficult to image well, because it is so diffuse and it's so much fainter than the bright solar disk. And so by placing the secondary mirror out of the light path, it means that we're able to keep that light path as clean as possible and reduce as much stray light that we might get from the spider effects from suspending a secondary mirror in the light path. So once we reach the secondary mirror, the light is passed through a series of pretty complex optics and are fired down into the bottom half of the telescope. So if you can advance again, John, we'll be able to skip forward to the other half of this image. And down below, you can see a platform that has lots of boxes on it. And so this is what we call the Kudai Platform. And I think this is one of the really innovative and cool aspects. The whole telescope is really innovative and cool, but this piece I think is particularly exciting because this whole platform, this entire section of the observatory, and you can see, we have some people in here for scale. This entire platform rotates with the sun. So as the sun moves overhead, it appears to rotate in the sky. And when you're taking super high resolution pictures of the sun, you can't have it rotating, or your images or your data will be blurry. And so rather than trying to remove that blurring in post processing, they actually move the entire telescope system underneath the sun to compensate for that rotation, to make sure we're getting really crisp, clean images right from the very beginning. So the other piece of this picture that I want to point out is just behind the this rotating platform. You might be able to see a little box with two people in it, and this is where our telescope operators sit. So these are the folks who are doing the commanding of the telescopes. This is not something that you have people moving about in while the telescope is in operation, because safety concerns, as you can imagine, are top of our priority list. So our operators are separated from this from this area. They're able to look into the area safely and make sure everything is the way it's supposed to be, and they have all of the safety and shutoffs and everything ready to go in case something needs to be stopped at the last minute. But they are the folks who are driving the telescope on any day-to-day basis. So in my opinion, they have one of the most exciting jobs of the entire observatory. Okay, well, if you can move on to the next slide, John, please. This is a close-up of the Kudai lab that I mentioned. This is the rotating instrument platform. So I want to make sure that it's very clear that this is an artist's impression. The actual platform is far more complicated than this and has optical benches spread all over it, and it is quite the sight to behold. But this gives you an idea of roughly how the platform works. So the light comes in from above, and it gets passed through a series of mirrors and through our adaptive optics system, which helps to compensate for any changes in the solar atmosphere. And then the light gets divided between, at the moment, 4 or 5 different science instruments. So we can use up to 4 instruments at the same time. And we have one instrument called the cryo nurse, or cryogenic infrared spectropolarimeter. It rolls off the tongue. We just call it cryo-NIRSP. And this will be the instrument that images the corona specifically. But because they're looking at the corona, and we mentioned already that this is very, very difficult to do, they're actually using lines that have to be imaged using cryogenically cooled instruments. So we have to cool them right down to be able to see into the infrared part of the solar spectrum. And so that instrument, at the moment at least, will work on its own. And the other 4 instruments can all work together to be able to look at the same part of the solar atmosphere or the solar surface in lots of different ways. So the instrument that took the pictures that we released last year is called the Visible Broadband Imager. And if you move on to the next slide, just for gratuitous glory of looking at how pretty these pictures are. We will get to that in a few minutes. So these are photographs of the actual telescope. So I don't know about you all, but I'm always stunned by how industrial research telescopes tend to be. They are built on scaffolding, and they have a lot of electronics exposed, and it is very unlike the kind of elegant tubes of the 19th century. These are very much a research laboratory kind of feeling. So in this picture here, you can see the back of our primary mirror. So the shiny side that reflects the sun is on the other side that you can't see right now, but you can see all of the wires that are attached to the back of this mirror. And these are actuators. They're little push-pull buttons that move in close to real time to compensate for effects of the atmosphere and of gravity. As you can see, the whole mirror is tilted on its side. And so with something that large, remember that's 13 feet tall, something that large, you're going to have some gravitational effects. When it needs to be polished to the degree our mirrors need to be polished, every little aberration makes a big difference. And so these actuators on the back push and pull to try and compensate and reshape the mirror in real time. If you go forward again. And this is the other side of that picture. So this is looking at the front side of the primary mirror. So close to the center left of the picture, you can see what looks like a white ring with it almost looks like it's see-through, but that's because the reflecting surface is so sharp. This is the primary mirror. And then in the very center of the picture, you might be able to see just a really small white spot. And that's actually the reflected light coming from the telescope. So the light is coming in from the aperture, it's bouncing off the primary mirror, it's going through the heat stop in the secondary mirror, which is up at the top right. And you can see all those tubes that are designed to pull the heat away from the telescope to keep it as temperature controlled as possible. And then because this was during the testing phase, they put in a little sheet here in the center to just show that the sun is reflecting smoothly and clearly where they expect it to. So in operations, this little card will be taken away and the light will continue down the rest of the light path. And if you can move forward one more, John, please. This is one of my favorite pictures of the telescope. You can think of this as if you were sitting with your back to the primary mirror, looking up towards the secondary mirror and the heat stop. And then the circle that you can see with the little blue slice, this is our aperture. And you can just see how beautifully clear the skies are above the telescope. So this to me signals hope and excitement of what the future is going to bring for solar astronomy. And then I had started to mention, if you go forward again, that we would just take one last gratuitous look at the pictures from the Inouye Solar Telescope, because they really are quite mesmerizing and quite hypnotic. So I think the video might look a little bit choppy here today, but I encourage you all to go to our website, nso.edu, and these pictures are all available on our webpage for you to look at. They're also on YouTube and social media and many other places, but these, I think you could probably look at them for a long time and just get blown away. And so as I mentioned earlier, this is of the solar surface. So this is looking at the visible surface of the sun. And in this particular picture, we don't see any images that are, or sorry, we don't see any features that are particularly familiar. We see a lot of this detail and the little white strings. These are magnetic features and so on. But if you move to the next slide, we also released a picture of the first sunspot taken by the Inouye Solar Telescope last fall. And so sunspots are features that you may have been able to see through your own telescopes. So I'm going to spend just a minute or two talking about different solar features and how we see them. So it's really important in solar astronomy that we use multi-wavelength observations. So we can't only look at visible light. As I mentioned, we'll also look at, if you can go back one, John, please. We also look at infrared light and at ultraviolet light and at white light. And there's all of these together paint the full picture of the sun's behavior. And so if we can go back to the picture on sunspots, I just want to mention a few little features of sunspots that might make it interesting. And John is going to speak in a few minutes about how you can safely view the sun. But a sunspot is part of the solar surface where the material in the surface has literally been pushed out of the way because magnetic fields are bursting through the surface and making it so that the solar material can't sit there. Can you go back one slide, John, please? And they appear dark. Okay, they appear dark because they contain less heat because there's less material than all of the surrounding areas. They're still very, very hot. They're still in the thousands of degrees, but they are because there's less material there, they contain less heat, so they emit less light, and they look like they're dark. And they have some really beautiful features and structure. And if you can see some sunspots through your backyard telescope, if you know or binoculars safely, of course, I should say, making sure that you use safe solar filters, they really are a sight to behold. If you have eclipse glasses, provided they are still in good shape and that there's no holes or anything, and I encourage you to go to the American Astronomical Society webpage for safety on using different safe solar materials, and John will speak about them as well. But if you have eclipse glasses, you're able to use eclipse glasses to actually see what we call naked eye sunspots. So never look at the sun with your naked eye, but it means that you don't need magnification. And we don't get many of these. We might get one or two every 10 years. I remember one in 2014, and I feel like there was one about 18 months ago, but I can't quite remember. Time is meaningless after the last 12 months. But as you can see in this picture, there's lots of structure and there's really lots to see. So these are best seen using H alpha or white light telescopes. And John will speak more about this in just a little while. Okay, if you can move forward one, please, John. And this moves us on to the next solar feature, which are solar prominences or solar filaments. And something I think that is largely overlooked is that prominences and filaments are actually the exact same thing. And they were named two different features because when they were initially discovered, scientists didn't realize that they were looking at the same feature because they look so different. So if you're looking at a filament, this is a long, generally dark feature that is on sort of imprinted on the visible disk of the sun. And if you're looking at a prominence, then it is a bright feature that is sticking off the edge of the sun. And we often see prominences using backyard H alpha telescopes, and these are definitely some of the more beautiful things and easy to spot things during, especially solar minimum, when there's not a lot of solar activity going on. But the thing is that a solar filament is actually the same feature. And so this movie is not playing right now, but maybe we can share some of these on in the chat window afterwards. Oh, you can start to see it here. So because the filament is generally cooler material than the rest of the sun, it looks dark. So an analogy to this would be if you had cold hands and you held a hot cup of coffee, your hands would start to feel warmer, but eventually your coffee would get colder. So if instead of it being just heat, there was also light, your hands would be absorbing that light from the hot cup of coffee and making the cup of coffee look a bit cooler. And so the filaments behave in a similar kind of a way where they're absorbing light and heat from the surrounding areas. They're absorbing energy from the surrounding areas. And because of that, it makes those areas look a little bit darker. However, if they are protruding off the edge of the sun, there is no heat for them to be absorbing in the night sky. And so they look really bright. They're the brightest thing in that particular area. So it's all about contrast. What is hotter or cooler than everything else around it, and that's sort of how we distinguish between solar features. So these features are generally best seen using a H alpha telescope, and especially prominences. These are the ones that stick off the edge of the sun and are really quite beautiful to behold if you get a nice clear view of them. Okay, and if we move on to the next slide, please, we're going to talk a little bit about solar flares. So unfortunately, solar flares are extraordinarily difficult, nigh on impossible to see from a backyard telescope. These are extremely energetic features. They tend to happen in a very quick manner. So they happen over tens of minutes and they release about the same amount of energy as like atomic bombs. So these are huge eruptions of energy and of light. And this is an important distinction that I think, again, is often overlooked, is that solar flares and coronal mass ejections, which we'll get to in just a second, are two distinctive features. Often they happen in conjunction with each other, but not always. And so the solar flare part is the light, a bit like a flare you might set off in an emergency. It's just a big eruption of light. And that's what a solar flare is. It happens when the sun's magnetic field gets tangled up on itself and it essentially short circuits and energy gets moved around really quickly and in a huge volume, and it emits enormous bursts of light and often other forms of energy. And because of the fact that it's so high energy, it's generally seen in higher energy ends of the solar spectrum. So in extreme ultraviolet and X-rays and gamma rays. On the very rare occasion, like the Carrington event in 1859, you can actually see a solar flare from the ground using visible light, but they are extraordinarily rare. And so I wouldn't necessarily count on being able to see one of those from the ground. And so these are, as you can imagine, best seen using satellites. And that's because so much of the emission that is ejected from or emitted during a solar flare is absorbed by the Earth's atmosphere. Thankfully, that keeps us safe. And so in order to see them, we have to go above the atmosphere where this emission is absorbed. And if you can go on to the next slide. We're going to talk about coronal mass ejections. And coronal mass ejections, I think, are often confused for solar flares, but this is during one of these solar eruptions, this is the stuff, this is the material, the particles, the high energy particles, the magnetic fields that get ejected into interplanetary space. And this is the material that travels through space and often hits off the Earth's magnetic field, and that's what causes space weather events and aurora borealis and australis and so on. And so these are they're enormous structures. So if you think about how small the Earth is in this picture, it is, perhaps the size of 2 or 3 pixels in the center of this picture. That, or maybe one of the stars would be about the size of the Earth, and how big these features are. So if the Earth is in the way, it's coming towards us. This happens all the time, and it's not something that we need to be alarmed about. It is something that we need to be prepared for. And so things like electricity grids, communication satellites, and so on, these are all important parts of preparation. And actually, this particular event was from 2017, and it was directed at Earth. And it happened at the same time as Hurricane Irma, which hit the East Coast and caused quite a lot of devastation. And as a result of this coronal mass ejection, the radio frequencies were interfered with. And so emergency responders actually had a hard time communicating with each other for a little while the solar flare was happening. And so this is the reason that we need to be prepared for space weather, and put in time and effort into understanding what causes them and how they behave. And we still have a very long way to go in doing that, in being able to predict these readily, but we're certainly making decent progress. So these coronal mass ejections are best seen, they're easiest seen either from space using space-based occulters. So an occulter is basically just a disk that you move in front of your camera to block out the bright light of the sun, so you only see the edge. It's essentially an artificial eclipse, or from the ground. So I mentioned earlier that the Inouye Solar Telescope is going to be able to study the corona, and we have a LEO stop which will be able to do that. And so certain ground-based telescopes are well equipped to be able to image the sun's corona to see what emissions are coming from it. So I think at this point, this brings me to the end of my segment of the presentation, and I'm going to hand it over to John, who's going to continue the conversation about solar viewing and how best to observe the sun yourselves. So thank you for listening.
So hey everyone, so I'm just going to go over some safe ways to observe the sun. Claire just talked about how we can actually see sun using through the atmosphere, visible sun, sunspots. And this is one of the pictures that I took in 2017, and I had to zoom in quite a bit. You can see that sunspot right in the center, just below the center of the sun. And that was, I could see that with my own eye. Using a telephoto lens just made it a little better. You can look directly at the sun, but only while wearing these cool eclipse glasses like this group that we had in Oregon with us during the eclipse. It's the only way you can safely look at the sun with your own eyes. Regular sunglasses won't cut it. Those space blankets, they look like filters, they don't cut it. And we'll go over some of the other things that you can use. You can use a solar filter. This is a filter that's specially made for the end of your telescope. It's a piece of mylar, really, aluminized plastic, and it's engineered to a specification, the ISO. Oh shoot, I had it written down and I lost it, but it's engineered to a certain ISO standard to be safe for your telescopes and your eyeballs. One of the only, we also want to protect our telescopes. I can tell you one of the things that I've done in the past is use these projections. And just like the Inouye Solar Telescope, we are focusing a lot of light onto a piece of screen so that we can look at the sun. This is how people map sunspots. We've been doing this for several hundred years now, since Galileo first observed sunspots. We still have people that actually project the sun's image onto a plate, and they'll draw out where the sunspots are. They'll catalog them and classify them, and it's still an ongoing science. You can create a pinhole camera. It's really this simple. You poke a hole through a piece of paper, and you project it onto the ground. You can do this using a box where you can put your head inside the box. You have a pinhole camera, it projects it on the back of it. Again, don't look at the light, look at the projection of the image. These aren't good enough to see sunspots, but they're good enough to, during an eclipse, you can get an idea of what's going on, where the moon is in the path of the sun. And you can also use it during transits. If you've got a big enough, if your eyes are sharp enough, you can actually see, tiny little Venus, tiny little Mercury moving across the sun. There's also a thing that I create, or I didn't invent this. It's called a sun funnel. This is the one I built, and it's cost maybe $10. You can get a funnel from your hardware store. You attach it to your eyepiece. You cut off the bottom. You get a piece of film for the top, like something you would use for a projector, that screen material, and you can focus that image. You can see the moon is halfway across the sun, and during this eclipse in 2017, and you can share it with a lot of people at once. You don't have to worry about them moving the telescope, looking through the eyepiece. This thing was totally automated, following the sun, tracking the sun, and it worked out pretty well. And you can actually see some sunspots, the same sunspots that you saw in that original picture that I showed of looking through the atmosphere. This was just a couple days later, and it was kind of cool. People really liked this. One of the main issues with this, though, is I can't tell you how many times, if I was using a piece of eyepiece that was not all metal, there's a lot of heat, and I melted several eyepieces pretty good. So there's that danger. There's also a thing called a sunspotter telescope. This is a brand name telescope. The light comes from the left side. There's a eyepiece or a lens there, and then it bounces off a mirror in the corner, the far corner, bounces back to the left bottom corner, up to the top corner, and then down projects this image. These are actually really good, again, for large groups. They cost a couple $100, or you can build them yourself. And they're kind of a neat little gadget to share. You can also use it to trace. You put a piece of paper into that area, and you can draw where the sunspots are. So it's great for public outreach events or class events when you've got students. Really fun. One of the coolest little gadgets is an H-Alpha telescope. One of the most popular brands is a Coronado. This is the one we use to share with the joys of looking at the sun. The sun in the same sort of ways that the Inouye Solar Telescope does. The sunspots we saw before, like in the sun funnel, are just white light. The H-Alpha telescope actually shows us the grassy structure, the rough structure of the sun itself. They're a little hard to tune, but they're super, super duper cool to look at with groups of people. And again, this thing is designed to look at the sun from the top to the bottom, and so they're totally safe to look through. You can attach a camera to the end of it, and you can get some really great pictures that way. Again, you've got to deal with the atmosphere, the Earth's atmosphere, so the images aren't quite as crisp as what we'd see from space, or with the adaptive optics on the Inouye Solar Telescope and other solar telescopes, but still a great tool to use looking at the sun. So some tips. Some of these are just, they're common sense, but never ever look directly at the sun. Your eyes, it's not just the heat, it's the ultraviolet radiation. You can damage the cones and rods in your eyes. So we want you to be safe looking at the sun. We want you to keep your eyesight so you can continue looking at the night sky. Always inspect your solar filter, the ones that you put, either it's the eclipse glasses or the ones you put at the very top of the lens. If they're scratched or damaged or punctured or anything, don't use them. They're cheap. We can replace them. Children always need help with solar glasses, the eclipse glasses. One of the things I do is show them look at the ground, put your eclipse glasses on, then look at the sun. It's so bright that you'll see it instantly. And they think they're going to lose it, but they don't. But they need help. If you normally wear eyeglasses like myself, keep them on because you want a clear shot of the sun. You can put your eclipse glasses over the top, or you can hold the handheld viewer. You can actually use a big filter from the end of the telescope and hold it up to the sun and look that way through it. So that always goes between you and the sun. Don't wander around with your eclipse glasses on. You look super cool in them. We don't want to see you trip. It's never cool. To remove them, you just reverse the process. You look back down at the ground, take them off. Don't look back at the sun. You can look directly at the sun during a total solar eclipse, but if any part of the sun is showing, please don't look. That little bit of light is very concentrated, just at 99% of the eclipse. It's very concentrated, and it can really do some serious damage to your eyeballs. Definitely don't look through the sun through an unfiltered camera, telescope, binoculars, anything that focuses the light, that focuses right on your eyeball. I mean, that's what it's designed for. It's focusing there so you can see it clearly. You do that, you're going to burn out your retina just instantaneously, almost. It's funny, in the night sky, we don't have to think about these things, but during the daytime, I get stuck with how I deal with nighttime astronomy. And I've burned holes in t-shirts and shirts because I wasn't being as careful as I should. So it really demands an protection. Say it over and over again. The solar flux goes between the sun and you, always. So if you, I have some links up here, and Andrew's going to share these on out to the group. You can follow us newsletter. It's on almost every page of our website. You can reach us. You can email us always. If you have questions, outreach@nso.edu is the best way to get to us. Happy to answer your questions. If we don't know the answers, we have scientists who are great at explaining things, and we will get the answer for you. And heck, who knows, we might create a video that we share to the world. You can find Twitter at @NatSolarObs, and Instagram, YouTube. We put out social media material all the time, just celebrating and explaining sun science for everybody. We also have our blog, just nso.edu/blog, and follow us however you like. We'd love to hear from you.
That's fantastic. Hey, wow. That's thank you very much, John and Claire. That's there's just so much stuff that I learned from this presentation, the details of this telescope. I mean, I think like most people out there, I've seen the picture, that was, I think it was in New York Times. And I remember it's just the chatter that came about, but then, you don't, that was a big spire, and then everything's kind of quieted down out here. So this is really great. There's some amazing things coming in the pipeline then that we should be watching out for, I think. Claire, tell us, what should people be looking? I mean, we're going to go on the website. We're going to go and follow. I'm definitely going to follow your social media and keep up to date. But what can you give us a little hint of when and what we could expect?
So I'm not going to be able to give you too many specifics because we still are not entirely sure of the specifics. So with COVID, everything has kind of been thrown up in the air, and we're still working out what the timeline is going to look like. My understanding is right now that they're working towards wrapping up the construction side of the project, which is it's an active building site, and everything is still very much under development by the end of this year. What will happen then is we'll have a 12-month commissioning period, and during that commissioning period there will be active science conducted. So earlier this year, the science team or the telescope team put a call out to the research community to say, hey, we are going to have these instruments ready to use. What studies would you like us to run? And so there was a few hundred people applied for that, and they narrowed it down and made the announcements of which studies were successful a little while ago. So during this commissioning period, they'll be running those studies. And so I'm very, very hopeful that during that period of time, we'll also be able to get I won't say frequent, because we have to sort of wait and see how things come out, but at least a more frequent release of new images and new data, because the images that we've seen only come from one of the 5 instruments that we have at the telescope, and so the other 4 are very much more on they're the academic research end. They're polarimeters. They're looking at kind of complex data that's coming through, and so the images, I think, from the visible broadband imager are really the sort of the jewel in the crown of these really gorgeous pictures. So I realize that I'm not really giving you an answer by now, but I'm hoping spring to summer of next year, we will be able to start getting more frequent updates from the telescope. That was supposed to happen this year, but like I said, COVID delays put everything on hold and meant that all of this got pushed back by close to a year. So fingers crossed this time next year.
Of course, of course. And we have a question here, Claire, from Sarah. And she's asking, is there any way you can tell how much radiation is hitting the Earth? With all the recent rockets punching through our ozone, just wondering if the radiation is increasing. I guess she's talking about the solar radiation from the sun.
So that's a great question, Sarah. Thank you for asking. There's actually quite a few instruments, a few satellites that are dedicated to just that measurement. The one that I'm most familiar with is on the Solar Dynamics Observatory, and it measures the amount of radiation coming from the sun towards the Earth pretty constantly over time at lots of different wavelengths as well. And so, even though we have lots of rockets going up into the atmosphere, our atmosphere is very robust and it has many layers. And even as a rocket leaves the atmosphere, it's a gas. So it's a bit like if you were driving through fog. The fog doesn't leave a hole behind you where your car once was. It just sort of moves back to fill the void, fill the gap. And so that's not something that we need to worry about as a result of increased space travel, or increasing space travel, I should say. And the amount of radiation coming from the sun is something that's pretty well understood. It varies with the solar cycle, which happens every 11 years. And it's something that I think the science community has a pretty reasonable handle on. And so that, how that plays into our understanding of Earth climate and so on, because the solar cycle varies on a period of 11 years, that tells us a lot about the likelihood of, how it fits into climatology and so on. But there are definitely satellites that are dedicated to studying this on a daily basis.
And Claire, it's funny. Sarah says, thank you, makes me feel much better.
Good. That's one of the things that I think, with increasing news and social media and so on, it's easy to be inundated with new information that you may never have realized before, or one may never have realized before. But we also have to remember that the sun and the earth have been existing in harmony with each other for a very long time. And so just because we're becoming more aware of it doesn't mean it's becoming more dangerous. It has more of an impact on like our technology and our way of life, perhaps. But as far as it being like physically damaging to humans, we have a very robust atmosphere. We have a very robust magnetic field, and those two things are our shields against any harmful effects coming from the sun. So as long as those two things are it's stable, then we're in reasonable shape. And this is a reason why there's a lot of folks who are sort of studying the cross between solar effects on different planets. I know that Mars is another case study for, Mars has a much thinner atmosphere, much sparser, weaker, almost non-existent magnetic field. It has these like magnetic bubbles that kind of exist in pockets. And so it's, they're able to use that as like the, where would Earth go if this was if we lost either of these. And so, we're able to use the other planets and even sometimes solar systems around us to better understand our own environment, the same as we can use our environment to understand the rest of the universe also.
Yeah, I mean, it's very interesting that you bring that up because we are looking at other planetary systems beyond our own and other stars. How is our clear? Just to put it into perspective, as a person who follows all these exoplanet, news that's coming out, and we're ranking up all these possibilities of, what are the conditions necessary for possibility of life around other stars, and I hear words about solar flares, some of them being very dangerous and potentially not too friendly towards life, especially like things like red dwarfs and things like that we look towards when we're analyzing exoplanets. I guess my question is, how does this research that we're doing here on our sun impact when we're looking for other habitable planetary systems and what those stars are, how friendly they could be towards life or unfriendly?
That's a great question, and actually, one of our researchers at NSO is his speciality is just this, and so understanding the solar or stellar magnetic activity of your host star, it turns out, is a really important factor in how sustainable life might be. We think about life on other planets and habitability, and we think about water or oxygen or the things that our bodies need to survive, but we don't necessarily think about the external influencing factors. And so if you have a very, very active star that is producing, tens or hundreds of very large solar flares daily or weekly, that it's high solar activity or stellar activity, I guess, technically. If you then don't have an equally robust magnetic field around that planet, then anything that it lives on that planet will just be irradiated. And so, there's these additional layers of plausibility of what is likely to be survivable or not survivable that we have to take into consideration when we're looking at extrasolar planets.
Yeah, it's fascinating. It's the connection that's so important. We can't disassociate. It just says we can't disassociate these sciences of looking at, our sun, or even looking at other planets. Like, we're so interested in exploring Mars, and then how they are, how everything is connected within the solar system. And now we're finding that everything that we're learning about our sun and our planets have implications in our understanding of other star systems out there. It's all connected. You all follow the same physics, right, of the universe.
Absolutely, and it happens on all scales. So it happens, in the cosmos, happens in our backyard. It's all different scales, but the rules of physics apply throughout. And yeah, I mean, that's one of the beauties, I think, of studying the sun, is that it, like I mentioned earlier, it is the Rosetta Stone for the rest of the universe. What we understand about our sun, we can then apply to other stars. And I remember somebody telling me, giving me an analogy when I was an undergraduate student, and we were talking about the Hertzsprung-Russell diagram, which, for anybody not familiar, is sort of a picture that encompasses the life cycle of a star and how it, and the different ages and styles and types and colors and temperatures and so on. And they said that if an alien species came and took a snapshot of the planet Earth, if they look at one human, they would know very little about the human race. They would know how tall one human was, how old one human was, what color hair that human had. However, if they took a snapshot of the entire human race at the same time, they would have a really good understanding of, roughly how tall do humans grow, how old do they live, what types of hair, all the different features and characteristics that the human race has. And so I always think of the HR diagram being that equivalent, where we can only study, even if we study a single star for our entire lifetime, that's barely a second in the lifetime of the star. It's hardly a blip in their life cycle. But by looking at all the stars, then that gives us a much better understanding of all of what's happening in the universe and how all of the stars can evolve. And of course, there's always outliers. There's always stars and humans that break the rules. But it gives us a good understanding of generally how things move. And the sun is an important part of that understanding and kind of our anchor in how we fit into the larger scope of things.
Amazing. Everything's connected. We've got
Mm-hmm.
a question from Norman from the Philippines. And he's asking, do we expect improvements in our flare forecasting methods with the expected data from Inouye and complemented by Parker and Solar Orbiter data?
That's a great question. So, yes, and this is a kind of a complicated question. The Inouye Solar Telescope, as I mentioned earlier, is giving us data that we have never seen the likes of before. And this is really important because it allows us to make sure that our models, the theory behind our understanding, is as accurate as it can be. And by making our models and our theory as accurate as we can be, that then feeds into our ability to forecast solar flares. So the Inouye telescope itself won't be fed into, for example, the Space Weather Prediction Center, but it will be used to improve the understanding, the research understanding that then ultimately leads to improved forecasting. So it's kind of a yes with a little asterisk attached to it. But yeah, the day that we released the pictures from the telescope, some of our theorists at NSO, they've been studying the underlying physics behind this. And for folks who may not be familiar with how this works, we use our understanding of physical processes to build a computer simulation of what we think is happening in the solar atmosphere. And then we use data to sort of flip back to say, yep, that looks right. These compare really well, or, well, this is too big or too small or too wide or whatever it might be. And then you go back and you adjust your physics to make sure that it's as clear and as accurate as you can be. But if you don't have the pictures, the actual data from the sun to be able to compare to, then you're sort of looking at something and squinting and saying, well, I guess that maybe looks like it could be a good fit, but because you don't have the clear pictures, then we can't be sure. We can't be absolutely sure. And so the Inouye Solar Telescope data is giving us those crystal clear pictures that we can then look at the models and look for issues or areas that need to be improved upon, or where they look really good, where are they on point, and then we're able to take that understanding and say, okay, well, now we know what the physics is, and now we know what the drivers can be, and now we can do better flare predictions.
Right. Very interesting. And of course, while observing the sun, it's not only in the realm of scientists. John, you pointed out very clearly that this is something that fascinates people. But I think there's something, like what you pointed out, there are ways that people, the average person, can connect to. I mean, yes, we have the technology of going on the internet and seeing what these wonderful professional facilities are doing, but there's also some way that we can also connect and observe as well, but do it safely. And this is, I think, something that people maybe feel daunted a little bit about observing the sun. There's this little bit of a fear factor maybe in terms of, well, we all learn we're not supposed to look at the sun and look away. And there are many places in the world where there actually is a discouragement of of doing that and observing, but there are very simple ways, right? I mean, John, it's not hard to do it safely.
Well, no, it's right there. I think one of the hardest things for nighttime astronomers or any observers, anybody who's used to observing, we're so primed to look at nighttime, at galaxies and clusters and nebula and stuff like that, that we look at the sun and we go, it's kind of boring. And, honestly, every 11 years, we just came out of a solar cycle, the minimum, where there wasn't but maybe 40 days last year, maybe less, where there were sunspots on the sun. So not much to look at the sun, but there are instruments that we can put in on our telescopes, such as the H alpha filters and things like that, that make the sun a lot more dynamic to look at. And if you follow the sun over several days, you can start to see it as an evolving system, something that changes daily. And, you can watch this, you can track this, you can get on our website and look at the images that we create. Like Claire said, our Gong network, we have 6 telescopes around the world that look at the sun every minute of the day. And we've been doing that for 40, 50 years. So we have a lot of data. So we can look at the historical trends, we can do that. You can be part of this. It's like one of the easiest citizen science projects out there.
Well,
can
this is it.
I add to that?
Yeah,
Real
go
quick,
ahead.
just as far as John's mentioning of the Gong network, there is another resource that is, if you're unfamiliar with the sun and want to do a bit of sort of early research or just checking it out to see, there's a website called helioviewer.org that it filters images from many different satellites into its viewer, and it's made for the well, it's used frequently by the public. It also has a research component to it as well, but you can put in any date and it will show you pictures of the sun on that date, and you can change the wavelengths, and you can look at the surface, or you can look at the atmosphere and all the different layers and so on. And it's a really cool way to just play around and just get to know what the different elements of the sun. And also to just sort of reiterate what John mentioned during his presentation, that most companies that make telescopes, you can buy a solar filter specifically for your telescope. It's really important that your filters fit your telescopes really, really well. You don't want any gaps in them. And the safest and easiest way to do that is to just call your telescope manufacturer and say, hey, can I get the solar filter for my telescope? And then it comes, and it's very easy to put on. Of course, don't forget to cover your eye, your viewfinder, because that is also a little mini telescope. But that makes it, if you're wary or if you're anxious about it, that's like a surefire way to make sure that you're getting a quality product.
This is very interesting. While you're mentioning this, Claire, the sun is becoming more active. And you can see here at our friends at spaceweather.com, one of my favorite websites. Look at what is lately there, right? There are sunspots visible. How big are those right now? This is what we see today. If it's clear and this is
Yeah.
what you, how big are these?
So they are probably too small to see with the naked eye. You might be able to see them if you had binoculars or a telescope with a solar filter on them. I doubt they're big enough to see with just eclipse glasses. I think they probably would need a little magnification. They're about the size of planet Earth. So, that's the
Wow.
Even though they're small, they're still pretty huge. But yeah, from here until we expect the peak of solar maximum to be in about 2025. So from now until 2027, expect lots of really cool solar activity, lots of solar eruptions, hopefully lots of big, bad, and ugly sunspots. And I mentioned during the presentation that the sun's magnetic field is kind of the driver of this. And there's, maybe in a different presentation, or you can probably Google this online, that the sun's magnetic field wraps itself up over the period of the solar cycle. And then it starts to unravel itself by this reconnection process that I mentioned, like shorting out over the other half of the solar cycle. So that's why we get this like building up to solar maximum and then reducing down to solar minimum. And that process takes, the whole process takes on the order of about 11 years, which is the solar cycle. So we're now at the stage where the sun is getting all tangled up again, and you're going to start to see these sunspots bursting out through the surface, and then they're going to start erupting and becoming solar flares and coronal mass ejection, and we'll start to see more solar activity, and then eventually it will have detangled enough that it'll start to become calm again, and then that's when we'll return to solar minimum, probably 2028, 29. So you've got like the guts of a decade for being able to see some good solar activity.
Well, it's just amazing. This is, again, this is from our friends at spaceweather.com. I like going there, checking things out, what's happening in terms of space weather. And of course, a lot of that is driven by solar activity. And, as someone who is an amateur astronomer, I'm an amateur, and, I love watching the sun too, but it's been very quiet, like what you guys have said. There hasn't been too much activity in the last year because of that minimum in the 11-year cycle. So it's really exciting for me as a backyard stargazer, amateur astronomer, love the idea there's something that's visible and easy to see. And it's not, you don't need a large telescope, right, John, to equip with. You put your solar filter, you get one of these, nice safe solar filters. You don't need a big telescope to see sunspots like what's in these images, right?
Not at all. You can, even if you had a filter for your binoculars, you could easily see sunspots there. Of course, the bigger the telescope, the more resolution you've got, so the sharper the images will be. But I have a little 3-inch refractor. That's what I've grew up with. I had an even smaller reflector before that, and with the projection method, uh, I could see all the sunspots I wanted to see when I was a kid. And now, when I take my telescope out with, I now have a larger 12-inch reflector, and I have this big solar filter that I made myself and put on the top of that, and it works fantastic to see. If I was want to watch it every day or every couple days, a sunspot will move across the disk of the sun in about 9 days. So you can actually, catch it at the edge of the sun and watch it even change day to day as the sun rotates that sunspot around. So it's kind of cool to watch.
It is. It is. This is, this is what I'm jazzed about the sun always, and it's just because it's always there. It's something that we can see. It's very accessible, and with just some simple careful methods, you can really do a lot of amazing, of not just observing, but it's a learning opportunity, especially I think for youngsters too. This is an opportunity, a fantastic opportunity to learn. Eclipses, of course, are of the sun, for instance, are again something. It's a wonderful opportunity for everyone to really be aware of their cosmic, location, of where things are, and the mechanics, the celestial mechanics at play. So I want to thank you, both of you, for coming by and sharing this wonderful, wonderful knowledge about the world's largest solar telescope, of giving us a taste of what its capabilities are and how it's really going to really transform our understanding. I think it's some of the sun and how it's connected to everything. It's fantastic stuff. And John, the tips on what people can do and how to get them, excited about going out and really learning more about the sun. It's our star. It gives us life on our planet, and it's something that we should really all appreciate. So thank you to both of you. We've got links, everyone watching out there. Here's quickly again links to everything that we've been talking about. Let me put them on the screen here. There you go. These are all the. We'll have them in the comment section for everyone, so we can go and follow the National Solar Observatory. They're on Facebook, Twitter, Instagram, of course, YouTube channel, and there's so much exciting stuff to come from all of you. Thank you again for joining us, John. Take care. Thanks so much for being here, and we'll be in touch, I think, again.
Thanks
and
for having
Claire,
us,
same
Andrew.
to you. Thank you so much.
Thank you.
Bye-bye, guys.
Bye.
And folks out there, thanks again. We've got links to everything that's happening in Global Astronomy Month. Today is SunDay. If it's clear where you are and you've got a solar telescope, go out and watch. I'm actually seeing there are sunspots visible right now. So the solar activity is picking up. So it's really cool. We'd love to see your member reports too. So do sign up for on our website, astronomerswithoutborders.org, our GAM calendar of all of the events. And there's still events to come. Tomorrow, Monday, April 26th, come for our Cultural Astronomy Facebook Live special. We'll be talking about the Mapuche culture and their cosmic vision in Chile. And of course, the Rapa Nui in Eastern Island. On Easter Island, the ancient astronomy cultural vision there will be covered by very special guest speakers. So that's on Monday, April 26th. You can find that on our calendar. And of course, on April 29th will be our cosmic concert that will be put on by Giovanni Renzo in Italy, composer. Every year, fantastic concert put on for Global Astronomy Month. It's the world's largest astronomy festival. I hope you've been paying attention and getting involved and sending us pictures. We'd love to hear what you're doing for Global Astronomy Month. Again, all of that visible on the link just down below in the comment section. So I'll see you on the next video. Until then, I wish all of you clear skies. Bye-bye.
From the pale blue dot to the distant stars, we are one. One people, one sky.